My name is Luis Sanchordorki. In this talk, I will give an overview of the physics motivations for experiments at the Forward Physics Facility, including both standard model and beyond standard model physics. The FPF will probe physics that span multiple frontiers, but because of time limitations, I will concentrate here on the searches for new particles and dark matter. And after that, I will go over some aspects of high-energy astroparticle physics. I will end with some conclusions. So let's jump into the first part of this talk, which is mostly based on these three articles down here that you can consult for further details and references. I would also like to thank my friend Jonathan Fang for allowing me to reproduce some of his slides in this presentation. The ATLAS and CMS detectors are designed to find new heavy particles which are produced at rest and decay isotropically. However, as more and more high-energy data are being collected and analyzed at the LHC, the high mass reach of strongly interacting particles has become saturated. Our best chance to discover new physics is to look in places that have not been explored before, and this means weakly interacting light particles. Now, these new light particles are mainly produced along the beam line, and so the particles disappear through the holes where the beams comes in. So what we need is a detector to cover the blind spot in the forward region. High masses and weak couplings are also complex, but are unlikely to be accessible in the near future. So this is the particle physics way of looking at things. We can also look at things from the cosmological perspective, where we have some hidden sector that has some dark matter in it, and this hidden sector communicates with the visible sector through a portal, let's say a dark photon, which can be characterized by a mass m and a coupling epsilon. And so what we can do now is compute the interaction annihilation cross-section, which parametrically goes as the coupling square, and by dimensional analysis scales as the inverse of the mass square. Now we can simply ask, where in the mass interaction strength plane we have the right thermal relic density. And we find that up here there is too little to be dark matter, and down here we have too much to be dark matter. And it is along this band, diagonal red band, where we have the right amount to be dark matter. And we know that this diagonal coincides with the frontier of high-energy physics experiments because it spans the parameter space of the well-known Wave miracle. Now, this parametrization shows that the region where new experiment can probe is along this band, again, that goes down with slope 1, roughly all the way to here, the region of the weakly interacting light particles. So it is just an incredible coincidence that the cosmological motivation and the particle physics motivation line up so beautiful in the mass interaction strength plane. Now, the dark photons may decay to visible particles, but only after traveling long distance. So the particle velocity is near the speed of light, and the rest lifetime is enhanced by the small mass and the small coupling. The lifetime is further enhanced by the time dilation. So this means that these particles will travel on the order of 100 meters roughly for couplings of 10 to the minus 5, masses of the order of hundreds of MeV and energies of TeV. Altogether, weakly coupled particles imply long lifetimes, whereas low masses typically makes particle production to peak in the forward direction. So optimally, what we need is a precision spectrometer looking into the forward region of LHC collisions. But of course, we cannot place a reasonable size detector on the beam line near the interaction point because it will block the proton beams. However, since the particles we are looking for are long-lived and weakly interacting, we can place a detector far upstream along the line of sight after the beam curves. And this is the idea behind the forward search experiment phase. This experiment has been installed 480 meters out from the Atlas interaction point and will start taking data during LHC run 3. With a decay volume roughly 3 orders of magnitude larger than phaser, the upgraded phaser 2 detector of the forward physics facility will operate during the high luminosity era. Now we can ask ourselves how big this detector has to be. And we find that for a pseudo rapidity of eta equal to 9, the opening angle is about 0.25 milliradian. This means that most of the signal passes through one sheet of paper at 480 meters. To appreciate the physics potential of phaser 2, we are now going to examine in detail a specific model. The dark sector need to talk to us, but if they do, the question to us is, what are the most likely non-gravitational interactions? I'm going to assume again that we have a dark sector, a U1 dark force, dark electromagnetism. Generically, the force carrier of the standard model F mu nu and the dark electromagnetism F mu nu prime will mix. Now, there are many standard model dark sector interactions, but the most popular one is induced by arbitrarily heavy mediator. And this goes through loops that naturally give me the small coupling. The renormalizable Lagrangian density is of this form with the standard model and a dark sector. Here we have the part of the dark photon, and we leave unspecified here the part of the Lagrangian for the interaction of the dark photon with these heavy states of the hidden sector. So a priori, we have 3 unknown parameters, which are the mass of the dark photon, its coupling, and the branching of the dark photon into these dark states. But if all the states on the dark sector, on the hidden sector, are massive, then there is no phase space for the photon to decay into the hidden sector, and the photon, in the dark photon, will decay into the visible particles. The production of these dark photons is through meson decay and dark bremsstrahlung. Here we have examples, production through pion or eta decay and the bremsstrahlung here. The guys then will propagate 480 meters in the case of phaser, and then will decay to visible standard model particles, but after a long time to do it exactly on top of the detector. Indeed, the luminosity at the high luminosity LHC, the expected luminosity is 3 inverse attobar. And we know, using hadronic event generators, that the amount of pi zeros that they are going to be produced is 4 times 10 to the 17. There will be 6 times 10 to the 16 etas, 2 times 10 to the 15 Ds, and 10 to the 13 B mesons. So we have a huge number of dark photons that they can be produced. And now we do a simulation, and we see how many will survive the trip to the phaser detectors. And here on the right, we have the sensitivity plotted for phaser, and phaser 2, again, in the mass interaction strength plane. The dark areas here, the gray shaded areas, are excluded by previous experiments. So we see here that both phaser and phaser 2 have some region which still is unexplored, and they will be sensitive to. So far, we have left the strengths of the kinetic missing completely unknown. And completely model independent. So I will now consider a specific extension of the standard model within the context of little string theory to see what we can say about the mixing parameter. So in this model, the enormity of the Planck mass is attributed to a tiny string coupling, okay? So the hierarchy problem here is equivalent to understand why the coupling of string, why the string coupling is so small. Despite the small string coupling, since the standard model lives on Neveu-Schwarz 5 branes, the standard model couplings are order 1. The U1 prime, the dark photon, lives on a D7 brane that wraps 4 cycles of volume. So the standard model generically is neutral under this U1 prime. And this is an example of the secluded U1 symmetry that I discussed before in that previous Lagrange. The U1 prime will develop a mass through a hidden standard model singlet Higgs field. And this hierarchy will be invoked. We will need to invoke a hierarchy between the vacuum expectation value of this Higgs singlet and the string scale. And this hierarchy rises as the string scale to the 3-half. We can calculate the U1 coupling, and here we have the expression. And then, as I said, this the mixing is generated via loops of these guys, the heavy states that have mass m sub I. And then with all that, we can go and compute the mixing. We compute the mixing, and we find that for string scales that vary between 10 to the 5 and 10 to the 7 TeV, we have an overlapping region between this unexplored region in which the FPF phasor 2, more explicitly, FPF experiment phasor 2 will be sensitive to, and that the little string model is predicting some signal. So this means that the FPF experiment phasor 2 will be able to probe string physics. So the dark sector may include more than one mediator particle coupled to the visible sector. Standard model gauge and Lorentz symmetry greatly restricts the way in which mediator can couple to standard model interactions. The portal relevant for dark sector which interact with the standard model depends on the mediator spin and parity. And here we have some organizing principle that give you these specific examples. We just show the spin 1 dark photon, and the FPF experiment, phasor 2, is not only going to test the spin 1 case, it's going to test also the spin 0 dark Higgs, the spin 1/2 sterile neutrinos. And if you want to know what is the sensitivity, you can go, as I mentioned, to this paper. The process is very similar to the one I just discussed before. What's more, dark matter particles could scatter inside the FPF dedicated neutrino experiment, producing visible signals. These neutrino experiments are phasor nu2, the advanced scattering and neutrino detector, and the forward liquid argon experiment FLARE. For example, elastic scattering of dark matter particles may be visible as an excess of neutrino-like event over the standard model yield. On top of the rich experimental program to search for scattering of dark matter particles, the forward microcharge search detector Formosa is primarily targeted at probing the kinetic mixing portal, which allows dark matter from a hidden sector to become visible by acquiring a small electric charge. This is what we often call millicharge, and we know these particles generically as mini-charge particles. So Formosa will reach sensitivity to charges as low as 10 to the -4 of the electron mass. This means that Formosa will have sensitivity to particles with masses on the order of 100 MeV to 100 GeV, roughly something like that. And indeed, it will become the experiment with the best sensitivity in this region. So if you want to look at more details on Formosa, flare, and how these dark matter searches or Millet charge searches are done, you can go again to this white paper that we prepare for the snow mass exercise, and it's available down here. And this concludes the first part of the talk.